So if I've got a pointer to the next block, then I can go and look at that previous block and check that it points back to me. And those were the checks that were introduced into the user mode heap. And what we did in Windows 7 is we simply added these into the kernel mode pool as well. They'd actually been there for a while in check builds as a way to help developers catch bugs. But for Windows 7, we added these into the normal retail builds as well. So that means now that if you corrupted any pool memory in kernel mode on Windows 7, that would get detected and the system would bug check. One of the good things about that is reliability, whereas before you might have hard to diagnose bugs because depending on how the headers have got corrupted, you might fail in different ways, kind of maybe a long time after the corruption. Now, whenever that corruption is detected, you would bug check. So hopefully you'd pick up these bugs earlier on. And one of the things people worry about when we propose security improvements inside of Microsoft is clearly the performance impact that those are going to have. One of the good things about the pool checks is the main cost associated with performing all these backwards and forwards checks is if you have to load in a page into memory that previously wasn't there. Now you're doing that anyway because when you're removing one page from memory, you're going to be updating the forwards and backwards pointers of the surrounding blocks. So the few extra instructions to check the integrity weren't going to be significant. Another thing that was mentioned earlier was compatibility with existing applications. What if there was some driver out there that happened to rely on overwriting headers in the pool? Well, the good news is that no driver should really be doing that, and that would be a completely bad thing to do. That would probably have resulted in unstable behavior anyway. So in this example, compatibility wasn't an issue. So this is one example of a bulletin where doing this kind of thing would help. It was a tool overrun in TCP/IP.sys, documented in Kostya's paper, and the root cause is an arithmetic overflow inside a loop. So you can see the source scan variable is only a 16-bit variable. There was a for loop that was kind of warping a chain of objects, and if you ensured that chain of objects was longer than about 65,000, then this source count plus plus would go up to 65,000, 65,500 or whatever, and then it would wrap around to 0. And then you would allocate kind of 0 bytes of memory. So suppose this wraps around, that means that the amount of data to get allocated would end up being computed something very small, say 4 bytes. You would allocate 4 bytes, and then a little bit further on in the loop, you would start copying memory into that tiny buffer you'd allocated. And you'd go through that same for loop 65,000 times, copying all that memory. So you'd allocate a tiny 4-byte buffer and write thousands and thousands of bytes of data. Of course, safe unlinking would detect the moment that you kind of go beyond the allocated block size and start overwriting other heap headers. We talked to a number of people who'd developed exploits for this case on how they might kind of get around it, and their feedback was that it would make it immeasurably harder to exploit. Like we said before, it doesn't mean it's impossible. It just means that, to the best of our knowledge, we don't know people who successfully got around that, and it definitely does make the environment and the constraints on the attacker much more severe. One thing that's mentioned at the bottom, this only applies to those pool blocks where safe unlinking takes place. There are also bits of kernel memory that don't have this forward pointer, backward pointer check. And there's some frequently used blocks of memory that are in a singly linked list, for example. And so those are still currently unmitigated. And because they're just a singly linked list, we've got no way of checking the integrity. And there are a couple of other enhancements for Windows 7 in terms of addition entropy. So this is the future. I'm not quite sure what the status is of Visual Studio 2010, but this is about some work that we did there. So like I mentioned before, by the time Vista shipped, we were feeling reasonably confident about Stack Overflows. And that's partly because the first incarnation of GS had been back in 2002. There's been a long history of people trying to bypass that, and we'd successively felt that we'd managed to close those bypasses down via SEH, via improvements to GS itself, via DEP and ASLR. So this was released on 1st of January 2007, and on the 10th of April there was a triply exploitable Stack Overflow relating to the parsing of ANI cursor files. So you would create a web page. Your web page would say, I'm using this flashed ANI file so that my user sees a dancing pig instead of a little white arrow that says cursor, and that ANI file would get parsed, and if you'd supplied a malicious ANI file, you could trigger a Stack Overflow. So what had gone wrong? Well, the function that was vulnerable to the Stack Overflow had no GS protection. So I guess we probably looked so much, because in the past it had been so trivial to bypass the early versions of GS, we'd focused on closing down all those bypasses. But of course the other avenue was that not all functions get GS protected. And that was an area that we maybe neglected to look at enough. The compiler heuristic is kind of listed there, and basically a function will get GS protected if it has a buffer on the stack where the buffer is kind of chars and wchars. That was kind of the design. So if you've got a buffer and the element size is 2 bytes or less, so char buff 256 or wchar buff whatever, then that will get protected. And that was largely really just due to the initial design of GS. IE had gone to the compiler team and said, look, we're getting a whole bunch of Stack Overflows and strings, you need to do something to help us. So GS was initially really designed to handle string overflows. The thing that got overflowed in the ANI case looked like this.